All right, I'm going to be going over the problems with gas laws worksheet. So the first thing, before I get into it, that you have to know is that we're going to be working with this equation PV equals nRT. And you have to memorize that equation, so make sure that you know that. And R in this case is the universal gas constant. It's equal to 0.0821 liter atmospheres per mole Kelvin. And the units on that are actually really important because what that's saying is if we're ever using R, we need to make sure that all the other variables are in the correct units. So that means pressure has to be in atmospheres, volume is in liters, number of moles is always in moles, and T, the temperature, has to be in Kelvin. And so whenever we're plugging numbers directly into this PV equals nRT equation, we're going to make sure that the units are correct there. The other type of problem that we're going to be doing if you're not plugging numbers directly into this equation is one where you come up with a proportionality equation. And that's when you're going to have something changing. So we'll give you like an initial volume and an initial temperature, and it'll say, find the final volume, given that the final temperature is such and such. And so I'm going to go through and explain to you how to do that. So the example I just gave was between volume and temperature. So if you want to find a proportionality equation between volume and temperature, you need to solve the PV equals nRT equation so that volume and temperature are on the same side. So we'll go ahead and we'll rearrange this. And I get V over T equals NR over P. And so you can go ahead and cross multiply there if you want to verify that that's the same equation and that's right. But this is what we get, okay? And the idea here is everything on this side of the equation is a constant. And so that means when we take volume and divide it by temperature, we get some constant. And that allows us to create this proportionality equation, V1 over T1 equals V2 over T2. And what this is stemming from is we're saying volume divided by temperature always gives you some constant, always gives you some number that's always the same. And so if that's the case, the initial conditions, volume divided by temperature, will be the same exact as volume divided by temperature in the final conditions. So that's how this works. I'll do one more example for you. Let's say that we wanted a gas law between N and T instead. So we solve this and we get PV over R equals NT. So N and T are the things that we care about. The other things we're going to say are remaining constant. And so if that's the case, then we have N times T always being the same thing. So N1 T1 equals N2 T2. And you can create gas laws between any of these different variables. The more complicated ones are going to be something like P1 V1 over T1 equals P2 V2 over T2. You could even have 4 variables in the equation, but I won't ever have you have that case, but that's something that's totally possible. Something with this also to keep in mind is with the proportionality equations, we never have R involved. See V1 over T1, V2 over T2, and N1 times T1 equals N2 times T2. There's no R in there. So that means we're not locked in with liter atmospheres per mole Kelvin when we're doing these proportionality equations. You can put pressure in any units or volume in any units, and you get those same units back out. So you don't have to convert before plugging in one of the proportionality equations like you do when you're plugging directly into the PV equals nRT equation. But you do still have to make sure that Kelvin is the temperature, because in the temperature scale, Celsius is a relative scale. We need it to be Kelvin because Kelvin is absolute, meaning that it scales proportionately. 20 Kelvin has twice the energy of 10 Kelvin. That's not true for Celsius, because 0 degrees Celsius, that's the freezing point of water. Things still have energy at that temperature. There's still particles moving around and things like that. So we're always going to use Kelvin. And every time we plug in temperature, this unit, it needs to be in Kelvin. If we're using PV equals nRT, then we're watching units for the other things. It has to be liters and atmospheres and moles. If you're using the proportionality equations, you'll just get out what you put in. So that kind of summarizes what we'll be doing in this unit. So getting here to the problems, problem number 1, this one, if you read it through, you'll see that we don't have anything changing here. It's not like a before and after situation where we have initial conditions and final conditions. So this is just plugging into PV equals nRT directly. Again, because we're plugging in R here, and R equals 0.0821 liter atmospheres per mole Kelvin. You have to verify that all the units that we're plugging into this are correct. Pressure is in atmospheres. Volume is in liters. Moles is always going to be a number of moles. It's asking for the temperature, so we're going to get a temperature out in Kelvin. So it looks like things are ready to go. We can just plug these things in directly. Oh, 4 moles here, so we're good. So plugging things in here then, pressure 5.6, number of volume 12 liters equals number of moles is 4. R is always 0.0821. And then temperature is what we're trying to solve for. I'm not going to count for sig figs in this unit. I'm just going to round everything to 3 sig figs in the end. So that just keeps things simple, and that way you don't have to worry about all the sig figs with all the other complicated calculations and things like that you do. So you can go through and do the algebra here yourself. Solve for T. You get T equals 205 Kelvin. Problem number 2, this is talking about a gas. It says it has a pressure of 84 kilopascals, a temperature of 35, and then it says it's heated to 230, and it asks what the new pressure will be. So this is a very basic case of one where they're giving you a change here. We've got initial conditions and we've got final conditions. And you have to identify the 2 things that are changing. The 2 things that are changing here are temperature and pressure. So we have to solve the PV equals nRT equation to get pressure and temperature on the same side and everything else on the other side. So what this solves to is P over T equals nR over V. And then we say all of this is going to be constant. So we get P1 over T1 equals P2 over T2. That's our gas law that we have for this problem. So because we're not using PV equals nRT, we can just plug 84 kilopascals in here directly because this is a proportionality equation. There's no R in this, so it doesn't confine us to those units. Temperature, however, has to be in Kelvin, so we have to convert that 35 degrees Celsius to Kelvin. It's 308. That equals, on the other side, we're trying to find the second pressure. Second temperature, it says it's 230 Celsius. That comes out to be 503 Kelvin. And so then you go through, cross-multiply or do whatever you want to solve for P here, but you get P2 equals 137. And then the units that we have on pressure are going to be the same as the units that we put in for pressure. So since pressure was given in kilopascals originally, it's going to be kilopascals now. For problem number 3, this one says a container has an internal volume of 2,600 liters. The sun heats the container from a temperature of 20 degrees Celsius to a temperature of 55 degrees Celsius. What will the final pressure be? Assume that the pressure was initially 760 millimeters of mercury. So when you read this, it definitely looks like this is one of those cases where something's changing. And you have to ask yourself, what's changing? So think about that for just a second. Okay, so in this one, it's the temperature and the pressure that are changing. So it gives you this 2,600 liters. That actually isn't relevant to this problem right now because it doesn't seem like the volume of this is changing. So if we're looking at proportionality here, we're just concerned with pressure and temperature. Luckily, we just got the gas law between pressure and temperature in the last problem. We know P1 over T1 equals P2 over T2. So we're just going to plug that in directly. So going here, the original pressure is at the end, but it's 760 millimeters of mercury. Original temperature, 293 Kelvin. Again, make sure that the temperature is always in Kelvin. Equals the final pressure we're trying to find. Final temperature, 328 Kelvin. Okay. Solve for P2. We get P2 equals 851 millimeters of mercury. Question number 4. says how many moles of gas are in the container from question 3. So this one, we're trying to find number of moles. That's variable n. And because it's not asking about a change here, it's just directly asking us to find n, we're going to plug this into that PV equals nRT equation, just plugging it in directly. What we're looking for is n. We have everything else. Now, we could use, you might be asking, like, which pressure and which temperature do we use here, since we had two of them. I would suggest using the initial ones. You could use either one. It'll give you the same answer. But there are two advantages to using the initial one. The first advantage is that we were given those numbers and we didn't calculate them, so you don't have to worry about making a mistake in question 3 and having that throw off your answer in question 4. The other advantage is the initial pressure is given as 760 millimeters of mercury. That's a really easy conversion to 1 ATM. And so if you look up at the conversion factors up at the top, you see 760 millimeters of mercury is exactly 1 ATM. So what we have here then, if we're plugging things in, we have to get everything in the right units, but now it looks like they are. So pressure, 1 ATM. Volume, 2,600 liters. Number of moles is what we're trying to find. R is always 0.0821. Temperature for the initial conditions, 293. So we go through, solve that for n. You get n equals 108 moles. Continuing on here for number 5, read through it. You see that this is another situation where it's just plugging in directly into the PV equals nRT equation. So plugging things in here, we have to get things into the right units because R, remember, is liter atmospheres per mole Kelvin. You have to recognize 1,200 kilopascals is the pressure. If you look up at the top, there's 101 kilopascals per atmosphere, so we're going to divide by 101, and we get 11.88 ATM. The volume is 31 liters, that's already good to go. The temperature here, 87 degrees Celsius. That's the same as 360 Kelvin. Okay, and now we can plug things in directly. So 11.88 times 31 equals n, that's again what we're trying to find here, times 0.0821 times 360. We go through, we solve this for n, we get n equals 12.5 moles. Number 6 actually is pretty easy. If you read through it, you'll see that it gives you moles, it gives you volume, it gives you temperature, it asks what the pressure is. So you can see this is just one where we're plugging in directly. There's no change here happening, so it's not like a before and after situation. So we have PV equals nRT. All right, we need to plug things in. Pressure is what we're trying to find. Volume, 60 liters. N, 3 moles. R, 0.0821. And then we'll have the temperature of 400 Kelvin. And everything on this one is just nicely in the correct unit. So that was good on this one. We solve for P. We get P equals 1.64. And since we use PV equals nRT, the units that come out of that for pressure are atmospheres. Seven, also pretty quick and simple. The only thing that we have to do is convert that 56 degrees Celsius into Kelvin, so it's 329 Kelvin. And then we can just plug things in directly. So we'll get 0.09 times V, because that's what we're trying to find in this one, equals the number of moles, which is 7.7, times the gas constant, 0.0821, times the temperature in Kelvin, which is 329 Kelvin. Go through, do the algebra on that one, you solve it, you get volume equals 2,310 liters. Now you might have gotten 2,311, and the deal is I'm just rounding everything to 3 sig figs, and so that's why it says 2,310. All right, going on to the back here. This first one is actually sort of a two-parter, so if it seems confusing to you, it's because it kind of comes in two parts. So we've got a balloon. It says it's filled with air. Pressure is 1.25 atmospheres. Volume is 2,500 centimeters. It says if we take the balloon to the bottom of the ocean, pressure is 95 atmospheres. What's the new volume? And so on this one, the first thing we're going to do is set up a proportionality relationship between pressure and volume. And so what you always do for that is you set up PV equals nRT, and then you solve it so that the ones that are changing are all solved on one side, while pressure and volume are already on one side together. And we're going to assume the N, the R, and the T are constant. So the equation we get from this is P1 V1 equals P2, equals P2 V2. And then we just plug in the numbers that we have here. So 1.25 times 2,500. Notice I don't care about the units on volume here because we're not using R, so we're not locked into liters for volume. We can use centimeters cubed. 95 atmospheres for the pressure there, and then for the second volume, that's what we're trying to find, so that's V2. Solve there, you get V2 equals 32.9. And since we put in centimeters cubed, we'll get centimeters cubed out of it again. All right, second question here. It says, what will the new, it says how many moles of gas? So this is one of those cases where you could use the initial conditions or you could use the final conditions. But I'm going to suggest that you use the initial conditions because, as I said, you might have messed it up in your calculation here and you don't want to use the wrong answer from part 1 to do part 2. We're going to plug this into the PV equals nRT equation to find number of moles. But since we are putting it into PV equals nRT, we need units to be correct now. So we're going to convert this from 2,500 centimeters to 2.5 liters because there's 1,000 centimeters cubed in 1 liter. That conversion factor is on the top of the first page of this. So you'll be given all of those on the tests and things like that. So going through here, then PV equals nRT. So pressure at the top there, 1.25, times the volume, 2.5 liters, equals the number of moles. That's what we're trying to find. R is 0.0821. And then the temperature is 285 Kelvin. Okay, we solve for N. We get N equals 0.134 moles. Question 9, it says you've got 17 moles of gas at a temperature of 67 degrees Celsius and a volume of 88.89 liters. What pressure will the gas be? This one is one where we're just plugging directly into the PV equals nRT equation again. We have to make sure everything is in the right units. The only thing that we have to change here is degrees Celsius. It says 65 degrees Celsius, so we need that to be 67 degrees Celsius is 340 Kelvin. So we'll make that correction. Then we just have pressure times the volume, 88.89 liters, equals number of moles, which is 17, times R, 0.0821, times the temperature, 340. We solve here for P. It's going to come out in atmospheres because we're using the ideal gas law. So you get P equals 5.34 ATM. Number 10. This one says an ideal gas occupies 400 milliliters at 270 millimeters of mercury and 65 degrees Celsius. It says if the pressure is changed to 1.4, the temperature is increased to 100. What's the new volume? So in this one, we actually have a pretty intense set of situations here. So we've got 3 things that are all changing at the same time: pressure and temperature and volume. So when we solve the PV equals nRT equation, we want pressure, volume, and temperature all on the same side. So we say PV over T equals nR. These are going to be constant. So we know that P1 V1 over T1 equals P2 V2 over T2. Then we're just plugging in numbers. So 270 times 400 over 338 equals. Now I'll mention here, the pressure was given in millimeters of mercury. On this side, 270 millimeters of mercury. Here it was given in atmospheres. So we actually have to get them to the same units. So I'm going to convert that 1.4 atmospheres to millimeters of mercury. So we multiply it by 760 and we get 1064 millimeters of mercury. Because if you're ever using these proportion equations, you need them to be in the same units, otherwise the proportions don't work out. So it's 1064 millimeters of mercury there for the pressure, times the second volume, which is what we're looking for, and then the second temperature here is 373. You can go through, do the work on that one. You should figure out that V2 equals 112. And volume in this case is given in milliliters, so milliliters is our answer. All right, for problem number 11, it says, what's the volume when 23 grams of neon at 1 degree Celsius and a pressure of 2 atmospheres? So it's asking for volume. This one is one where we're just plugging into PV equals nRT. The 23 grams, it might be confusing to know what to do with that, but that's going to help us get to moles of neon. So what we do is we're going to take 23 and divide it by the molar mass of neon on the periodic table. We get 1.14 moles of neon. Celsius isn't the correct temperature. We got to put it into Kelvin, so it's 274 Kelvin. Now things are ready to plug in. So pressure, P is 2. Volume is what we're looking for. Number of moles. Here we've got 1.14 moles. That's what we calculated. R is always 0.0821. Temperature in this case, 274. So solve for V there. You get volume equals 12.8 liters. And that is that. All right. Number 12 is pretty straightforward too. We're just plugging into PV equals nRT, but unfortunately this one, they give you some really ugly units. We're given PSI, we're also given degrees Fahrenheit. Those are both kind of ugly things to deal with. So converting PSI, we divide by 14.7 to get it into atmospheres. So 32 PSI is equal to 2.18 atmospheres. The other thing we have to do is we have to get from Fahrenheit to Kelvin. So we have to go through Celsius first. So Celsius is equal to 5/9 times the Fahrenheit temperature, which in this case is 60 minus 32. All right, and we get 15.6 degrees Celsius. To get that to Kelvin, you have to add 273. So we get 288.6 Kelvin. All right, now we've got everything in the right units. We can plug it in. 2.18 ATM times volume. So the volume here is 40 liters. That was just given to you in the problem. Number of moles is what we're looking for. 0.0821 is R. The temperature is 288.6. All right, solve for N. You get N equals 3.68 moles. Problem number 13 is like that one above, where we've got pressure and volume and temperature all changing. So we're going to use that law P1 V1 over T1 equals P2 V2 over T2. Plugging things in, we have 700 times 600 over 297 equals 400 V, because the second volume is what we're looking for, over 278. Go through, solve for V on this one. We get volume equals 983 milliliters. (14), same thing. We're going to use that same equation. So P1 V1 over T1 equals P2 V2 over T2. Plugging numbers in, we've got 5 times 200 over 133. Now, this says we're at standard temperature and pressure in this problem. So you have to remember that standard temperature is 0 degrees Celsius or 273 Kelvin, and standard pressure is 1 atmosphere. So for the pressure here, we're going to use 1. The new volume is what we're looking for. Standard temperature, as I said, 273 Kelvin. So we go through, solve for V on that one. We get V2 equal 2,050 liters. Last problem here is relating pressure and temperature. So we start with PV equals nRT. Okay, we're going to have to solve it for pressure and temperature on the same side. So we get P over T equals nR over V. This is all constant in this problem, so we know P1 over T1 equals P2 over T2. Plugging numbers in, original pressure, 1 atmosphere. Original temperature, it's 100 degrees Celsius, so that's 373. Okay, P2 is what we're trying to find, the new pressure. The final temperature we wanted is 165 Celsius or 438 Kelvin. We go through, we solve for P2, we get 1.17 ATM. All right, that is that. I know I didn't go through a lot of the algebra in terms of solving for the variables here, so if you struggle with how to get the variable when it's an equation and trying to find the final value of it, come see me and I'll kind of try and walk you through some steps that you might take algebraically to get through that. I just didn't want to make this video any longer than it already is. So that's some algebra skills that I hope that you already have, but if not, I'll be glad to show you how to do that. So just come stop on by if you need any more help.